Hi, I am going to do a short video lecture to help you understand the topics in section 5.4. Now 5.4 is still all about polynomials, but now we're talking about graphing polynomial functions. So what I think I'm going to do is talk some about the graph of the polynomial that is shown there in example 1. And I'm going to use a little technology, so I'll be right back. I'm actually going to pop a graph of this thing onto my iPad so that we can look and talk, and I'll make it so I can scribble on it too. So give me just a second here to get it brought up. Sorry, it's asking for a software update. It only does that when I don't have time for it. Okay, I'm going to use my favorite graphing utility, which is not Pony Island, sorry. Desmos. I think you've seen me use this before. Okay, while this is going, what I'm going to talk about is why understanding graphing is important. A graph of a function gives us information about the solution set of that function, because the graph is really a picture of all of the points that satisfy a given function. So what we want to do, we want to understand the graph because it helps us understand how the function behaves in space over the x-axis. Understanding graphs can also help us understand how to solve an equation, because it helps us know where to look for solution points. Okay, so this is the graph of our function. Y equals x to the third minus 4x. And I am going to pop that in here so that we can scribble on it a little bit. Okay, what I want to do is talk about what your textbook is trying to explain to you in this first example in section 5.4. And I know I've got a little bit of glare there. I'm going to try to keep that to where it's not going to make any difference. Okay, the first thing that we want to understand when we're graphing a function is where the x-intercepts are. Now, x-intercepts are where the graph crosses the x-axis. So our x-intercepts are here, here, and here at the points -2, 0, and 2. Now, these are also the solutions to the equation y equals x squared, x to the third, excuse me. minus 4x. But remember, when we're on the x-axis, what does y equal? At each of these points here, y equals the same thing. This guy is negative 2, 0. The one in the middle is 0, 0. And this one out here is 2, 0. In all of these cases, y equals 0. So what we're doing is we're solving the equation y equals x to the third minus 4x. If you do that, you're going to find that y equals 0 when x equals negative 2, 0, or 2. We've already learned how to solve that equation. That was earlier in the term. Okay, so that's where those x-intercepts come from. Now, bear in mind, I use a graphing utility to do this. You won't always have a graphing utility, and sometimes you're going to have to sketch these things by hand. It helps to create a sign table. And I'm going to walk you through what that means. Keep in mind what this graph looks like. Maybe sketch it for yourself so you've got it for reference. And now let's walk through creating that sign table. So we are working with the function y equals x to the third minus 4x. We've already found our x-intercepts. To be at the points 0, 0, negative 2, 0, and 2, 0. Now, if we think back to our graph, let's take a look at this thing again. Let's envision dividing this graph everywhere. Well, not everywhere. Let's envision dividing it vertically at the x-intercept. So I'll show you what I mean. So let's say I put a solid line straight down that vertical line at x equals negative 2. If we look at our graph of our function, let me use a different color for my line so it's easier to see. Okay, so now let's look over here at our function. So this red line here represents all of the points that satisfy this equation, that y equals x to the third minus 4x. What I want you to notice down here is all of the y's are negative. So my y's in this region below x equals negative 2 are all negative. They're all smaller than 0 on this side of that x-axis or x-intercept. Now let's look between my first x-intercept and my next x-intercept, which in this case happens to be 0. So what we're doing is we're looking between this vertical line at x equals negative 2 and this y-axis. And you can see that in here, all of my y's are positive. If we keep looking and we look to the right of that x-intercept up to the next x-intercept, pretend it's as close as I'm going to get. All of my y's are again negative, and then they're positive. So what I want you to understand is that at each x-intercept, something happens to the y value. Now, in this particular function, the graph crosses the x-axis at each x-intercept. So that means that our y value changes in sign. It either goes from negative to positive or from positive to negative. sometimes it'll just, those are called crossing points when it changes sign like this one does. Sometimes it'll just touch the y-axis and go back up, or touch the x-axis and go back up or back down, kind of like a touch and go on a jet, if you've ever seen Top Gun. Whoops, sorry. Those are called touch points. And we can tell what we're going to get, whether our graph is going to cross the x-axis at a given x-intercept or touch the x-axis at a given x-intercept from the function itself. But we need to build the sign table in order to tell at this point whether we've got a crossing point or a touching point. So let's build the sign table for this function. Okay, so what we're going to do is we're going to make a chart, just like the one shown there on whatever page that is, at the page beginning of section 5.4. Sorry, I'm working on an electronic textbook and it numbers the pages separately for each chapter. So the first page of section 5.4, there's a sign chart at the bottom, and we're going to build that. Let me see if I can get my focus to lock. Okay. So what we're going to do, we make a row for each of our factors. So let me take this function here. I'm going to write it in factored form. And I'm going to make the presumption that you know how to do this and that you understand that this factored form is just another way of writing my polynomial. And what we're going to do is we're going to look at the sign of each of those factors. So I'm going to make a row for my first factor, which is x. And I'm going to make a row for my second factor, which is x plus 2. And I'm going to make a row for my final factor, which is x minus 2. Now, remember back to that graph and how I subdivided it. And what I'm going to do is I'm going to make a column for each of those regions. So we know that I've got an x-intercept at -2. So in here, this is going to be all x's less than -2. And what we're doing is we're putting the signs of the y, which is the same thing as a sine of f of x. That's what's going in our table. My next x-intercept is at 0, so this is going to be in this column, or in this region here, in this column. I'm going to put the sine of y when x is between -2 and 0. My last x-intercept is at 0, so I'm going to go between 0, and 2. And then we're going to look at x's that are bigger than 2. So let's think about this. And what we're going to do, we're not going to plug all of these things into my function. That's going to be, the sign of my overall function is going to be my last row. Okay, so think back to my graph. So for any x less than -2, that's what this is. So let's think about a graph here. And all I'm doing is thinking about the sign of x. If x is -2, and we can pick a point, say -3, what I want to know is x positive or negative. So if x is -3, that's negative. Is x plus 2 positive or negative? Well, we're testing -3. You can test any number as long as it is meets our condition. And what we set as for our condition is that x has, whatever number we're considering as our test case, has to be less than -2. I picked -3. So -3 plus 2 is -1. That's still negative. And now we do it for the third. We do the same thing for the third factor. -3 minus 2 is -5, which is still negative. So we don't really care at this point about the actual value. What we care about is positive or negative. Now, my function is made up of x times x plus 2 times x minus 2. So we can get the sign of our function by taking any negative number, multiplying by another negative number, we get a positive. But then we multiply by a third negative and we end up with a negative number. All we're doing is writing down the signs of the evaluation of these things in this region. This corresponds to the fact that our function is always going to be negative below -2. Okay, now let's consider between -2 and 0. I want a test number. I like -1. It's easy. I can't use -2 or 0. I can't use either of my endpoints. I have to use a value in between them. And I want to look at the sign of these factors in this region. So I've chosen -1 as my test case. If x is -1, that's negative, so the sign here is negative. If I plug -1 into x plus 2, -1 plus 2 is 1, so that's positive. And x minus 2, if x is -1, -1 minus 2 is -3. We just care about the sign, so just write down negative. Now, I need to multiply all three of those things together. A negative number times a positive number times another negative number will give me a positive number. So we know that my function is going to be somewhere above the y-axis. And we know it's got to come back down to 0 here, so it's going to look something like this. Okay? Let's keep going. Consider between 0 and 2. Let's use 1 as our test point. 1 is a positive number, so x is positive in this region. 1 plus 2 is 3. That's a positive number. So x plus 2 is positive in this region. 1 minus 2 is -1. That's a negative number. So x minus 2 will be negative in this region. A positive times a positive is a positive times a negative will give me a negative. So we know now that my function is negative. It has to turn around and come back to 0. And we're almost done. If we're out here bigger than 2, let's say 3 is our test point. 3 is positive, so this one's positive. 3 plus 2 is 5, which is positive. 3 minus 2 is 1, which is positive. A positive times a positive times a positive is a positive number, so our function keeps going. Okay, so that's the basics of the sign table. It's a tool that we use in order to estimate graphs of functions. All right. We're going to ignore my phone because I'm talking to you right now. Unfortunately, I don't know how to make it be quiet. There, they gave up. So this works no matter the degree of the function that we're talking about. And I just want to demonstrate one that's got a turning point. So let's look at example 3 in our textbook. And example 3 wants us to graph y equals x to the 4th minus 3x squared. What we need to do is write this in factored form. So I'm going to pull out an x squared. And I'm going to go ahead and factor this difference of perfect squares. I know we don't think of 3 as a difference of perfect squares, but 3 is square root 3 squared. So we can factor this as x minus square root 3 times x plus square root 3. And all I did was factor my polynomial. Now if I replace y with 0, I can see that I'm going to have x-intercepts at the point 0, 0, the point negative square root 3, 0, and the point positive square root 3, 0. Now, what I want to point out is that these each came from one of these factors. So remember to solve this. So if I'm trying to solve 0 equals x squared times x minus square root 3 times x plus square root 3, what I do is I write each of these factors as equal to 0. So x squared is equal to 0, or x minus square root 3 is equal to 0, or x plus square root 3 is equal to 0. I want you to notice that there is an exponent on that first factor. That turns out to be important and will help us determine behavior of the graphs without having to go through the sign. Well, we'll probably still won't go through the sign table, although I know you have a graphing calculator, so you probably actually won't go through the sign table, but I still think this is good to understand. So bear with me. I understand you're probably all just going to plug this into your calculator and graph it, but at least if you're ever stranded and need to graph a polynomial for some reason, you'll maybe in the back of your mind remember that this is how we do this. But that too, that exponent is important. It's called so this exponent gives us information. We call this a repeated root, because if we were to list all of the zeros out with, list each number individually. So instead of writing x squared, if I wrote x times x, I'd have to write 0 twice. So this exponent gives us the multiplicity of the root, or the 0. So 0 has multiplicity two, because the exponent is 2. Now, this root, or this factor, x minus square root 3, has got an exponent of 1, as does the x plus square root 3. So the square root 3 is a 0 with multiplicity 1. And the negative square root 3 that comes from this last factor has got multiplicity 1. Talk about this in a minute after I demonstrate what a touch point looks like. Turns out those multiplicities give us information about the touch points or crossing points. So let's build our sign table here. We've got a root, or a factor of 0, a factor of x minus square root 3, and a factor of x plus square root 3. And we're also going to look at the whole thing put back together. So I'm going to actually write that as x squared, not x, because x squared is my factor. And I'm going to have, my table's going to get a little crowded here. So let's see if I can make this work out. This is going to be all numbers less than my smallest root, which is negative square root 3. This is going to be between negative square root 3 and 0, and I'm using interval notation up here just to save space. This is going to be 0 to positive square root 3, and this will be everything bigger than square root of 3. Okay. All I care about are the signs. I'm not going to worry too much about the numbers. So square root 3. We know the square root of 3, so let's take a look at what is a square root of 3. (1.7). So the negative square root of 3 is negative 1.7. So let's use negative 2. So I'm just going to jot down up here what my test number is. So I'm going to use negative 2 as my test number. Negative 2 squared is positive 4. So x squared is positive. Negative 2 minus the square root of 3. Let's just test that. Negative 2 minus square root of 3 is negative. So that will be a negative number in this region. Now, negative 2 plus the square root of 3 is still negative. So this factor is also negative everywhere in this region. If I multiply a positive times a negative times another negative, I'm going to get a positive number. Okay. So the negative square root of 3 is negative 1.7. So I can use negative 1 as my test point in here, in this region. So negative 1 squared is 1. That's positive. Negative 1 minus the square root of 3 is negative. Negative 1 plus, whoops, wrong thing, square root of 3 is positive. So positive times a negative is a negative, times a positive is a negative. Move to the other side of 0, and we'll use 1 as our test point. 1 squared is 1, that's a positive number. 1 minus the square root of 3 is a negative number. 1 plus the square root of 3 will be positive. A positive times a positive is a negative. And we'll go ahead and use 2 as our test case out here at the far end. 2 squared is 4, that's positive. 2 minus the square root of 3 is a positive number. 2 plus the square root of 3 is a positive number. So our y's are again positive. Okay, so if we sketch this graph, and I'm not going to worry so much about exactly where square root of 3 is, I'm just going to put it on here. Below the square root of 3, my function is positive. So it comes down and does this. We know it's 0 at the square root of 3 because, or sorry, at negative square root 3, because negative square root 3 is one of my x-intercepts. Now, the function is negative between root 3 and 0. So my function goes all the way through, and we know it has to come back to 0, so it turns around. But it's still negative, so it must do that again. Go back down, and then turn around and come back up. Okay, this is a touch point. The function touches the x-axis at that point, but does not actually cross it. These two are crossing points. The function goes through the x-axis and the y's change sign. Okay. That multiplicity thing we talked about a minute ago is important because it turns out that touch points occur at zeros with even multiplicity. Even numbers, 2, 4, 6, 8. So when you factor a function, if you get a factor that has an even exponent, you know that the 0 that comes from that factor will be a point where the function touches but does not cross the x-axis. Crossing points occur at zeros with odd multiplicity. Numbers like 1, 3, 5, 7. So when you factor your polynomial, the factors that have got odd exponents will have zeros that correspond to crossing points, not touch points. All right. I hope that helps. There's some additional information in your textbook about how many crossing points and touch points you can expect for any given function based on their degree. Remember that the degree of a polynomial is the value of the highest exponent. In this case, my highest exponent is 4, so this was a 4th degree polynomial. The first example we did, the highest exponent was 3, so that was a 3rd degree polynomial. I hope you find this useful, and I will see you again soon with a lecture for section 5.5.